Welcome back everyone. So today we're taking a look at a whole bunch of code optimizations techniques to see what they do, and we'll also speak about related concepts. So last time we asked the question, how can the compiler improve performance? Well, one thing it can do is improve cache utilization. A big part of that is cache locality. So we want to access things that are stored together at the same time, and that's because these things will already be in the cache, and so it will be faster to access them at that time. Another thing we can do is to allocate register intelligently, because we don't control the cache. Each time we access memory, the cache gets filled automatically, but we do control registers, and so we could use them to keep data around that we will need. Something that is very important is to avoid bloating the code cache. It's important not to emit a lot of instructions, even if doing so theoretically makes the code faster in terms of cycle. And it's because all these instructions, they pollute the code cache. We also call it the instruction cache. And each code cache miss will cost you hundreds of cycles. Remember that accessing RAM is 200 times slower than accessing L1 cache, and the instruction cache is like the L1 cache. So yet another thing we can do is to avoid cache collisions by disaligning memory. We've seen last time that memory locations, they can map to the same cache line index. To avoid trashing the cache too much, caches have associativity, so it's 8 for the core i7. And that means that there can be at most 8 clashes before we start putting things out of the cache. However, even with an associativity of 8, clashes can still be an issue when we deal with things that are aligned to a multiple of the cache size. And in those cases, it can be useful to break the alignment to avoid trashing the cache and constantly writing the same 8 cache lines. Finally, another thing we can do is escape analysis. And so that's to avoid allocating heap memory that will be deallocated before leaving the function. Memory allocation is fairly expensive. It's not just a question of cache. Allocations are expensive. But we're also going to touch entirely new memory, so of course that's not very cache friendly. Another thing the compiler can do to improve performance is to improve the utilization of the CPU. And so that means avoiding pipeline stalls, which are times where the CPU sits idles and doesn't have instructions to process. So the most basic thing you can do is to schedule instructions intelligently, so by moving code around to fill the pipeline. Of course, you have to respect dependencies, so if an instruction depends on the result of a previous instruction, then you cannot reorder them. Something else you can do is parse your evaluation, in particular constant folding and constant propagation. Here the idea is that whatever we can compute at compile time, we don't need to compute it at runtime, so it's much more beneficial to do it at compile time. We have dead code elimination, the idea being that removing code that is unreachable makes the code cache more efficient and may also remove branches that could be mispredicted. Common sub-expression elimination, which is basically avoiding to recompute the same thing twice, which is only possible if the computation does not contain side effects, so writing to memory typically. Auto-vectorization is a technique where we automatically emit SIMD instructions to replace or complement simple loops over arrays. So remember that SIMD means single instructions, multiple data, and those are instructions that exploit data level parallelism. So basically we have a vector of values, and using a single SIMD instruction, you'll run the same operation on each entry in the vector, but in only one instruction's time. Finally, if we use a just-in-time compiler, the compiler is running on the machine where the code runs. And that means that the compiler is able to select the fastest instruction for that particular CPU. A third thing that compilers can do to improve performance is to remove obstacles to optimization. The big thing here is inlining, which enables further optimizations. And that's because optimizations are typically done within a function and not cross-function. So inlining helps expand what optimizations can do. The other thing we can do is cheat. So instead of optimizing one version of the code, we can make two specialized versions, which are each easier to optimize. One way of creating these is to move conditions outward, like the example at the bottom of the slides. So you have this code here, and you have two conditions that depend on x, and we go to this version here, where we have moved the x outwards, so there's only a single if now. So we now have a version that is specialized for x true here, and a version that is specialized for x false here. And those two will be much nicer to optimize. If you assume that all functions get inlined, now we can optimize the content of do3 with respect to x, but also with respect of what happens in do1 and do4. And in the other version, we can optimize do3 with the fact that x is false and with what happened to do2 and do5. In general, we want to eliminate conditionals and loops whenever possible. We'll get back to this. Compilers really like what we call basic blocks, which are sequences of instructions with a single entry point and a single exit point. So there is no jump going into the block and no jump inside the block going out of the block. Basic blocks are much easier to optimize, so this is a pretty important concept. So what does a modern optimization process look like? In the traditional pipeline that I've shown you a couple times, optimization comes right after semantic analysis. And after semantic analysis, we're still dealing with an abstract syntax tree, an AST, but very little optimization happens at the AST level. What will happen instead is that the AST will be converted to an intermediate representation, or IR, and that IR will be run through a series of passes. You can use the same IR for every pass, or a different IR after every pass. It depends a little bit. In Java's case, it's important to distinguish the Java compiler that takes your source code and emits bytecode from the just-in-time compiler, which takes frequently called bytecode and turns that into optimized machine code. And the intermediate representation of the just-in-time compiler is not Java bytecode. And we'll see an example of this later. So phases, or they're more commonly called passes, can be repeated. The idea here is that after you've performed some optimization, some other optimization that you couldn't do earlier now become possible. And the typical example is inlining. So you don't want to inline everything at first. So you inline some function. Then you perform constant folding on that and dead code elimination. Now your code has reduced in size, and so you might think that it's okay to inline more. And as you inline more, new optimization become possible, and so on and so forth. So this is just one example. There are many ways in which that plays out, with other things in inlining also. But the idea is that optimization enables further optimization, so it makes sense to repeat passes. So to concretize this is the example that we saw in the second video of the course. So you have this massive code here, but everything here is more or less fixed. So foo is false, so you don't need to compile this because it will never be taken. True is a constant, so you know that if you inline function b, it will return 42, and then 42 plus 1 is 43. So you go from this thing to this very simple function here on the right. Of course, optimization does not work on Java code, it works on the intermediate representation, but this gives you an idea of what optimization does. Okay, so now we'll talk about some optimization concepts, and then later we'll see some example of actual optimizations. So one very important concept is the static single assignment form, or SSA form. And this is a form used in intermediate representations where every variable is assigned only once. In practice, in your language, a variable might be mutable, meaning that it can be reassigned. And so the SSA form deals with this by creating new variable. So imagine that you have a variable x, and you assign to x multiple times. Then the SSA form will create a variable x1, x2, x3, etc. Why is this a good thing, the SSA form? Well, basically, it factors out work that is needed for many other optimization. So, to give you two examples, in dead code elimination, if nothing uses the initial value of x, then you can simply skip computing that value and storing it. For constant propagation, it is easier to reason about immutable value than it is to reason about variables whose value change all the time. So basically, by converting at the start of the optimization process into SSA form, we make every optimization that come after that much simpler. Well, not every optimizations, but many of them. There is an issue, however, And the issue is that if you have some code like this, so if condition x equal 1, else x equal 2, print x. When you go to SSA form, this will become if condition x1 equal 1, else x2 equal 2. But then what do you print? Well, you print x3, and you define x3 to be the result of calling a find node on the two variable in a condition. The idea of a find node is that it reconciles divergent assignments. And this is a trick, okay? So it's not like the SSA form is actually being executed. The SSA form is a notation that is used to perform optimizations, but at the end of the day, what will be emitted is not SSA form, it is machine code, okay? And there is no find node in machine code. But this trick makes the representation work, otherwise it wouldn't work. So this is just a very high-level overview of the SSA form. If you want to learn more, you can check this article, which is well written. It's also fairly introductive, but it will give you a deeper idea than simply this slide. Another concept that's quite important is data flow and control flow. And these will be encoded as graph, and these graphs will be used for performing various optimizations. So you have a data dependence graph, or a DDG, and this encodes data dependency. So if you're in your SSA form, you have x equals y plus z, this means that the value of x depends on the value of y and the value of z. Okay, so like I said, this is related to SSA, it just makes it much easier. The reason is that you want to include dependencies between data and not dependencies between variable, which may take multiple values. And the data dependence graph determines liveness. And liveness tells us whether the data is being used, whether it's being needed in the end. Next, we have control flow graphs. They abbreviate to CFG, so that's the same abbreviation as context-free grammar. Don't get them mixed up. And control flow graphs encode ordering relationships between instructions. So they say which instruction has to happen before which other. You can imagine the control flow graph running from the top to the bottom. And it will always go in that direction, except for loops. Okay, so loop jump back to the start of a loop. And such edge that go from bottom to top, we call them back edges. Control flow can also split, and control flow splits when you have a condition. Okay, you have one branch for the if part and one branch for the else part. And at the end, they merge so that you can go to the instruction that follows the if-else statement. Control flow graph, they determine reachability, and that tells you which instruction can be reached. So liveness and reachability, they can be used for dead code elimination. If a value is not being used at all, then there's no point in computing it. And if an instruction is never reached, then there's no point in including it in the compiled code. You might ask, well, if an instruction is not reachable, why is it there in the first place? And the answer is that that might happen as a result of other optimizations. Ordering constraints, they also limit instruction scheduling. So for instance, you cannot emit an instruction that computes some value if you do not have the value that it depends on. So let's see these data dependency and control flow concept at work. And the graph on the right here is the Graal IR for the code example on the left. Note that instead of being textual, the usual representation for this intermediate representation is a graph. And this is in contrast with something like the LLVM IR, whose representation is a linear sequence of instructions. So quickly remember that Graal is the JIT compiler that is included in the GraalVM Java distribution. The normal Java distribution uses a compiler called Hotspot, and Hotspot also uses an intermediate representation that is similar to this. So let's start by looking at the function. It has three parameters, condition x and y, and we'll refer to these by their indices. So condition is 0, x is 1, y is 2. We have a local variable, and depending on the condition, we will either assign a field to x and the local variable to x, or we will assign the field to y and the local variable to y, and then we return the local variable. Let's look at the graph. So we'll start by control flow. So there's a convenient start node. Then we have the if statements, and it splits into two branches depending on the condition. In both of these, we store the field. notice that there is no red box for these two assignments here. We'll talk about that. We merge, and then we return. That's it for control flow. Now for data dependencies. You'll forgive me, I think it's a bit small, but I will tell you exactly what happens in the graph. So in these round things, you have values. Here you have P0, P is for parameter, so this is the parameter with index 0, so the condition. Here you have C0, so C is for constant, and 0 represents false. Remember that in the JVM, there's no boolean, so we use 1 for true and 0 for false. And basically, you're going to run a equal operation there. And so if condition is equal to false, if that is true, that means that condition is false. So this is the false branch. And if it's false, it means that the condition is true. Okay? Slightly unintuitive. So if the condition is true, we're going to take P1. So that's the parameter is index 1, x. And we're going to assign it to the int field. Otherwise, we're going to take P2, so that's y, and assign it to int field. Next, at the bottom here, we have P1 and P2, so that's also x and y. And they're related to this phi node. Okay, here it is again. And it's annotated with from 15 and from 17. And those are references to nodes, and they are references to these two nodes. So basically what it says that if we came here, if in the merge we came here from the node 15, which means that condition is true, then the value for the phi node should be P1, so x. If we came here from 17, meaning the condition was false, then the value for the phi node is going to be P2, so y. And we are going to return that value. So what's really interesting to see here is that the storage in the field is included as part of the control flow graph, but the storage into the local variable is not. And the reason is that writing into a field is a side effect, because other parts of the code might be able to read from the field. Whereas writing to a local variable only matters for the inside of the function, so we are free to move that around. So for instance, this intermediate representation does not constrain whether this is actually calculated before or after assigning the int field. So if we had an advanced compiler class, we'd spend a lot of time here, seeing how to build this graph and what we can do with them. And they enable a lot of optimizations, and also sometimes useful semantic checks. In this video, I'm basically telling you what optimization exists, but I'm not telling you how to actually implement them and what data structures to use. And a big part of the answer is to use these graphs and to use SSA form. Like I said, this is what we would discuss in an advanced compiler class. According to me, it's less interesting than the rest of the course because you're less likely to implement your own optimizations. It's much easier to delegate that to Java runtime or to LLVM. The benefits you get from writing your own optimizations are not that great. You'll do it if you love it, but if your goal is just to make a language, then it's not a big priority. So now we are going to review a few optimization in addition to those we already talked about. So partial evaluation, we already talked about that, and I put it into scare quotes because partial evaluation can refer to the Futamura projection. That's what Christian Humer talked about in his talk, and that's when you take an interpreter and feed it into a specializer to make a compiler. What we're talking about here is the same idea, but on a much smaller level, and so mostly we're talking about constant folding and constant propagation. So whenever you have something that's constant, you can just do the computation at compile time instead of doing it at runtime. This can lead to dead code elimination. So when you have a condition that's probably false, you can just remove the whole condition. There are also other forms of dead code elimination, such as removing assignments that are never used or unreachable code. Something else you can do is that when you know the concrete type of a variable, you can bypass virtual lookups. Finally, you can remove runtime checks. So, for instance, the Java programming language does check array bounds each time you index an array. But if the array size is known to be constant, and if the index is known, then you can remove the array bounds check. For dynamic language, it's the same. If you're able to determine the type of variable, then you can remove the type check. So compilers hate jumps and loop. Why is that? Well, jumps may cause cache misses because you jump further ahead into the program. Conditional jumps may cause branch mispredictions, and we talked about those and how they cause pipeline stall in the CPU. Another thing is that it's harder to optimize a basic block that has multiple predecessors. The multiple predecessors means that it can be reached through multiple paths in the program. So in this example here, do3 can be reached after executing either do1 or do2. And so the issue is that in do3 you'd like to use assumptions on what happened before. And here you don't know whether do2 or do1 happened before. One possible optimization that we already talked about is that you would basically make two copies of do3 and put them in both branches of the loop so that you could specialize do3 for each case. You've got exactly the same issue in loops, where the code is potentially executed a lot, but you can only make assumptions that hold in every iteration, so you cannot specialize each iteration individually. And in particular, as we'll see later, it might be useful to detach the first iteration because something that happens in every iteration can then be used as an assumption for further iterations. Lucid Computer hate loops, but they also love loops. Programs spend most of their time in loops, and those are called hot loops, so those are loops that are called often. And so a lot of effort is dedicated to make the inside of loops as efficient as possible. And now we're going to see some example of that. So one loop optimization that exists is called loop invariant code motion. And an example of that is hoisting. That's when you extract code out of a loop. So in this example here, true equal true, that doesn't need to run for every iteration. So you can just run it once before the loop here, and that will be it. Another example of loop invariant code motion is to move code between iterations. So this is called global value numbering. And it's called like that because you assign numbers to values, and then you use those numbers to determine if the same values are being accessed. So to give you an example, you have a loop, and in the body of the loop, you are touching xi and xi plus 1 during the same iteration. What you could do is to move xy plus 1 to the next iteration, okay? And in the next iteration, it's going to be the same as xi, because I gets incremented. And so if you're able to move that operation to the next iteration, then you only need, for each iteration, to read xi. And so that's a single memory read, whereas before, for each iteration, you need to read xi and xi plus 1, so that would be two memory reads. Another important classes of optimization loops is loop unrolling. You can do multiple things. One thing you can do is to fully unroll statically bounded loop. So when you have a statically bounded loop, so for instance here you have a loop from 0 to 3, so you know it's only going to be run 3 times. Then what you can do is remove that loop and replace it by 3 invocations of the body of the loop. So this is basically inlining but for loops. Another thing you can do is to peel off the first iteration. So I alluded to this earlier. This allows you to take one iteration of the loop and to take what's in there and use it as assumption for the other iterations. And sometimes that can enable further optimizations. Another interesting one is called loop rotation or loop inversion, and that's when you replace something like while x and then the body of the loop with if x, do body while x. Why would you do that? Like, this seems more complicated. Well, the reason is that it avoids jump at the end of the loop. So if you think about it, in the last iteration of the loop, you execute the body, and then you will do an unconditional jump to the condition. You will check the condition, it will fail, and so you will do a conditional jump to the end of the loop. So you just did two jumps, basically going backwards and then forward. In this case, you don't do the unconditional jump because the condition check is at the end. And so you don't do this and that. So you save two jumps. And that's the whole point of this optimization here. More loop optimization. So you can do something called loop fission and something called loop fusion. And the goal is always to improve cache locality by either splitting or merging loops that have the same bound. So for instance, here we iterate on an array. And for each item of the array, we call the do1 function. And here for each item of the array, we call the do2 function. Then we can just fuse the loop together and do this. So sometimes you want to fuse the loops, and sometimes you want to split the loops, and that depends on the size of the array and depends on whatever these operations do. So do they access a lot of memory locations or not? The goal is always to improve cache locality. Other thing is loop unswitching. So if you have a loop with a conditional in it, you just move the conditional out and you make two copies of the loop. So we already talked about this. It's about specializing two versions of the loop. Of course, we always want a loop to be fast because they run many times compared to conditions, so it makes sense to move the condition outward. Another thing you can do is to identify the induction variable and use that to perform some optimizations. So the induction variable is the counter of the loop if you want. So for instance, in this loop, the induction variable is I. That's what's being counted. And I give you an example of optimization that you can do with that. So in this loop, we assign x to y times z each time. So this is a pretty useless loop, by the way. And so you could go to the optimization that instead adds z on every iteration. Okay, that's because the compiler was able to figure that I is the induction variable and increased by 1 for each iteration. So, doing this assignment is the same as adding z for every iteration. Of course, if the compiler is smart enough, this loop would just be removed and the compiler would just compile x equals 4 times z. But of course, you have to imagine that this is just a toy example and the examples are more complicated in reality. So it can do something like that in a loop that also has other operations, so you cannot remove the loop entirely. So there are some other very important optimization that we already talked about or mentioned. There's common sub-expression elimination. The goal is to avoid computing the same thing twice. And that's only possible if the computation doesn't introduce side effects. So side effects typically involve writing to memory, but there are a few other things like making system calls which might write to disk or do whatever. The opposite of sub-expression elimination is called rematerialization, and that consists in recomputing an expression instead of reading it from memory. That's to avoid reading from RAM, which as we know is very slow. That's when you compute something at the start of a function that do a whole lot of operations and then read from that location. And maybe the compiler thinks, well, it would be much easier to recompute that value than to read it from memory. Another that you might have heard about in other courses is tail call optimization. That converts tail recursive functions to loops. And so that removes the risk of getting a stack overflow if the function recurses a lot, and it avoids the overhead of function call. Another important optimization is escape analysis. And what that does is that if an allocation does not outlive the function, we can allocate it on the stack instead of allocating it on the heap just for the lifetime of the function, then deallocating it. And we already spoke about why that was important, because basically allocation is expensive, and then when you allocate, you touch entirely new memory, so that's bad for the cache. Some other optimization, alias analysis. This is an optimization for language with pointers, just like C. So basically, you have to ask a question, can two pointers refer to same or to overlapping memory? If two pointers are not referring to different region of memory, or if you cannot be sure that they are not, then you must take precautions. And in particular, what you need to do is that you need to wait for write to a pointer location to finish before writing to another pointer's location. And remember from the last video that memory writes were fast because we were just emitting the order, but we didn't need to wait for the write to actually occur. Here, we need to wait, and we'll have to wait a lot because we need for the write to hit memory. So this is only for languages with pointer, like C, so it does not concern, for instance, Java. And also, surprisingly, it does not concern Fortran, because in Fortran, the specification says that pointers can never be aliased. It's the job of the programmer to ensure that that does not happen. So if you alias your pointer by accident, then you might get some weird and very difficult to debug bug happening. But at least if you respect the rules, then your programs will be faster than they are in C by default. There's a keyword in C called no alias that you can use to say, well, I've checked very carefully and I guarantee that these pointers are not aliased, but people tend not to use that very often. So another class optimization are peephole optimizations, and those are pattern-based optimization. And a subclass of that is strength reduction. So what strength reduction does is replace the use of an operator by the use of a simpler operator. So for instance, if you have x divided by 2, and this is an integer division, then you can replace it by x shifted 1 bit to the right. If you have something like x multiplied by y plus x multiplied by z, you can use the arithmetic rules to simplify that to x multiplied by y plus z, and now you have one less multiplication there. If you have 3 times x, you can replace that by x plus x plus x, because remember, addition is much faster than multiplication. So this is a strength reduction, as well as this. Another thing you can do is that if you see a push on the stack followed by a pop from the stack, you can just remove both things. And such nonsensical things might happen as a result of other optimizations. So there's not much to say about inlining beyond what we already said. Inlining is great, it enables more optimizations, we love inlining. So here's a question. Why don't we inline everything? There's a few reasons. One reason is the executable size. You're going to generate out of duplicate code, and that's going to make your executable bigger. One reason is compilation time. So we could optimize code to high heaven, but in the end, computers are fast and programmers are expensive, so you don't want them to twiddle their thumbs while the code is compiled. If you have a just-in-time compiler, then there's even a very real performance cost to compilation time. All the time you waste compiling is time you don't spend in the program, and also time during which the program is still running a slow version. But by far, the biggest issue is that inlining everything causes a lot of instructions to be generated. So for the same code, if we have more instructions, that will mean that the code cache will get filled faster, and that means that we get more code cache misses. And those are extremely expensive. Remember that reading from RAM is about 200 times slower than reading from the L1 cache. So we said that inlining was used so that we could optimize multiple functions together. Basically, we pull the code of one function into another function. If we don't inline, what can we do? Well, something we can do is compute per function properties. Here are some examples of these properties. Is the function recursive, either directly or indirectly? Does the function store its parameter anywhere? And is the function read-only? So is it a pure function that does not write to any memory location? Knowing a function is recursive could be useful to select which function to inline. Maybe you don't want to inline a recursive function because you know that you can't inline the whole chain anyway because it's going to recurse. That is unless you can do tail call optimization, of course. Knowing whether a function stores its parameter anywhere is useful for escape analysis. If you know that a function does not store its parameters anywhere, then it means that this parameter can still be escape analyzed and allocated on the stack instead of being allocated on the heap. And if you know a function is pure, that helps with common subexpression elimination. So we've ended our tour of the most common optimization and the related concepts. So what to take away from all of this? So here's our big question again, how can the compiler improve performance? And there's 3 key things it can do. Improve cache utilization, and it can do that by increasing the cache locality, so accessing things that are stored together at the same time. Or reduce cache occupation, so make sure we don't put too many things in the code cache. Another thing it can do is improve processor utilization, so make sure that the CPU keeps processing instruction and avoid pipeline stalls. And finally, we want to remove obstacles to optimization. So we want to inline and we want to make sure that the basic blocks are as big as possible. There are a few more takeaways that go over the things that we saw. We have seen what static single assignment form, or SSA form, is, and the point of it, which is to be an easier form to reason about for many optimizations. We have seen data dependency and control flow graphs. We saw the example of the GRAL intermediate representation with the red control flow graph and the green data dependence graph. We've seen the related properties of liveness, so when some value actually gets used, they are said to be live, and the property of reachability, so statements that can be reached through control flow are said to be reachable, and instructions that aren't reachable can be removed, and values that are not live do not need to be computed, as long as the computation does not have side effects. We've seen partial evaluation, mostly at a local level, so constant folding, constant propagation. A big theme is that compilers really like basic blocks, which are sequences of instructions with a single entry point and no jumps until the end of it. Programs spend most of their times in loops, so compiler will take great pain to optimize those. Some optimizations that are applied here are loop invariant code motion, loop unrolling, as well as loop fusion and fission. There are some other important optimizations, like escape analysis to avoid temporary allocation, common subexpression elimination, and tail call optimization. So when you optimize, side effects, so data mutation is your enemy because you can't as easily move things around or remove duplicated computations. Of course, inlining is an enabler for all of these optimizations. That's it for today, and in the next video I will talk about collecting profile information, how to use this information to optimize programs. See you all next time.